Now, in this video, we discuss horse and cart problem. We discuss horse and cart problem. Horse and cart problem. There is a cart connected with a string by the horse. Cart is connected by a string to the horse. So, horse pulled the cart in forward direction. Horse applied the force in forward direction on the cart. So the tension force T would act on the cart in forward direction. Then from Newton's third law of motion, to every action there is equal and opposite reaction. So cart also applied a force on the horse in opposite direction. Cart will also pull the horse towards his direction. So since this direction is opposite to the force applied on the cart, so this will be represented by minus T. Minus T. This is the tension force. In a string, the force act is called tension force represented by T. Now the horse pulled the earth by his feet in a backward direction. Horse pulled the ground by his feet in a backward direction. So the force act is F, and earth applied the force from Newton's second law of motion. Earth applied the force on horse in forward direction, and this is called reaction force. Force of reaction R. And since this reaction force R is inclined to the horizontal, so there must be two components of R. One is called horizontal component of R and another is called vertical component of R. There must be two components of R, horizontal component and vertical component. So T is the tension force applied by the horse, minus T is the tension force by which the cart pulled the horse, and F is the force by which the horse pulls the earth or pushes the earth in backward direction. And from Newton's third law of motion, in direction opposite to F, the force acts on the horse, which is called normal reaction, represented by R. So there must be two components of R. One is horizontal component, which is represented by H, and another is vertical component, which is represented by V. And there is also a force act on the cart, and that is called force of friction, which acts on the cart in opposite direction. Force of friction acts in the opposite direction. So the cart moves in forward direction when H, the horizontal force, component of force, will be greater than force of friction. Here we take the case that horizontal component of force H, the horizontal component of R, is greater than force of friction. F is the force of friction, which we study in detail about force of friction later on. So, a cart connected to a horse by a string. A cart connected to a horse by a string. A cart connected to a horse by a string, and the horse produces tension in the string in forward direction. The horse produces tension T on the cart in forward direction, and the cart pulls the horse by an equal force T. The cart pulls the horse by an equal force T. Minus sign only shows the direction. And horse pushes the ground with the force F in an inclined direction. Horse pushes the ground by force F in an inclined direction. And from Newton's third law, in a direction opposite to F, normal reaction, R is called normal reaction. R is normal reaction or simply reaction. R is the force of reaction or reaction force, which acts opposite to the direction of applied force, and F is the force of friction. And R has two rectangular components. R has two rectangular components. One is H and another is V. Now, horse moves forward when H is greater than F, and also when H is greater than T. The applied force in horizontal direction must be also greater than by the force of tension, by which the cart pushes the horse, or applied force on the horse. Now net force acting on the horse. Net force acting on the horse. Acting on the horse. So the force H acting in forward direction and the force T acting in backward direction. Then the net and H is greater than T because cart is going in forward direction. So the net force acting on the horse will be H minus T. H minus T is the net force acting on the horse. And this net force is equal to the resultant force. So net force H minus T must be equal to the resultant force. And resultant force means from Newton's second law, mass into acceleration. H minus P is equals to resultant force by which car moves, which is equals to M into A. The car moves forward if P is greater than F. Also, if P is greater than F, the cart moves forward if P is greater than F. The cart moves forward if P is greater than F. Applied tension force is greater than force of friction. So net force acting on the cart. This is the net force acting on the horse. Now we are talking about the cart. So the net force acting on the cart. Net force acting on the cart. So T is greater than F. So the net force must be equals to T minus F. And T minus F is equals to resultant force, which is equals to mass M into A. Here we have supposed M is the mass of cart and a small m is the mass of horse. So T minus F equals to the resultant force mass into acceleration. Acceleration for both horse and car will remain same. Now add equation first and second. Add first and second. So we get H minus T equal plus T minus F equals to M into A plus capital M into A. So T and T gets cancelled and H minus F equals to A is common, M plus M into A, and we find the value of acceleration. A equals to H minus F upon M plus M. This is the acceleration acting by which the cart moves in forward direction. Acceleration acting on the cart by which it moves in forward direction. Now the next topic which we discuss, that second law is the real law of motion. Means first law and third law of motion are contained in second law. First law and third law of motion first law and third law of motion contained in second law. Contained in second law. Therefore, second law of motion, second law of Newton's law of motion is called real law of motion. So since first law and third law of motion contained in second law, therefore second law of motion, therefore second law of motion is the real law. Now we study that one by one, that how first law is contained in second law, and also how third law is contained in second law. So from Newton's second law of motion, from Newton's second law of motion, from Newton's second law of motion, we know that force is equals to mass into acceleration. F is equals to mass into acceleration. From Newton's second law of motion, we know that force is equals to mass into acceleration. And in the absence of, here F is the external force. So in the absence of external force, means there is no external force, then m into a must be equals to 0, and mass never be 0, mass of a body never be 0. It means the acceleration is 0. So we conclude that if m into a equals to 0, it means acceleration is 0. So in the absence of external force, if a body is in rest, it will continue in rest and if a body is in uniform motion, in a straight line, then it will continue in motion. Then it will continue in motion in a straight line with a uniform velocity. So what is this? This is the first law of motion. And if there is no any external force acts on a body, it means acceleration is 0. And if there is no any acceleration acting on the body and the body is in rest, then it will remain in rest. And if a body is in uniform motion means also there is no acceleration acting on the body. So if a body is in uniform motion and if there is no any external force, then acceleration is 0. So it will remain in uniform motion in a straight line. So we conclude that first law of motion contained in second law. From second law, the first law of motion comes there. It means the first law of motion is contained in second law. Now we see how third law of motion is contained in second law. Third law of motion contained in second law. Now we see how third law of motion contained in second law. So suppose there are two bodies, body A and body B. So body A will exert force on B and it is given by FBA. vector. FBA vector means force acting on a body B due to the body A, and B will exert a force on A, and this force will be given by F of AB vector, means force acting on body A due to the body B. And from second law of motion, we know that F of AB, force acting on A due to the B, force is equals to rate of change of linear momentum. Rate of change means d by dt, and linear momentum means Pa. Applied force on a body A due to the body B is equals to rate of change. Rate of change is represented by d by dt, and linear momentum of body A means Pa, which is also written as dPA upon dt. Similarly, FBA is given by d by dt of rate of change of linear momentum of body B, which is represented by dPB by dt. So this is the FAB and FBA. Now adding these two, so F of AB plus F of BA is equals to d by dPA by dt, dPA by dt, and plus dPB by dt. When we add these two equations, we get F of AB plus F of BA equals to dPA by dt plus dPB by dt, which is also written as d by dt of Pa plus Pb. Pa is the linear momentum of body A, and Pb is the linear momentum of body B. And in the absence of external force, rate of change of momentum is zero. In the absence of external force, rate of change of momentum is zero. It means F of AB plus F of BA is equals to zero. This is the rate of change of momentum, and this includes that F of AB is equals to minus of F of BA. So this is the Newton's third law. So Newton's third law is contained in the second law. This was the second law. Applied force is equals to rate of change of linear momentum of a body. So we conclude that Newton's third law of motion also contains, the second law of motion contains the third law. So first law and third law is contained in the second law. Therefore, second law of motion is called the real law of motion. Now we discuss the case of apparent weight of a man in a lift. Apparent weight of a man in a lift. Apparent man on a lift. So we find the expression for acceleration in various cases and apparent weight of a man in a lift. Apparent weight means the weight which is not real is called apparent weight. And this derivation is most important because in exercise there is questions based on apparent weight of a man in a lift. So we suppose that let a man of mass M is standing on a weighing machine placed in a lift. Let a man of mass M is standing on a weighing machine in a lift. Man is standing and the mass of man is M. Man is standing on a weighing machine in a lift, and we know that actual weight of the man is given by mg, and actual weight of the man is given by mg, and r is the normal reaction. Actual weight of the man is represented by mg, which acts in downward direction. Weight always acts in downward direction, in the direction of acceleration due to gravity. So actual weight of man is represented by mg, and normal reaction acts in upward direction opposite to the weight from Newton's third law. Normal reaction is represented by R, which acts in upward direction. So normal reaction always acts opposite to the weight. If and weight acting downward direction, and normal reaction acts in upward direction. And this normal reaction is also called apparent weight. This normal reaction R is also known as apparent weight, which is not actual, apparent weight. Now the first case which we discussed, when the lift moves upward with an acceleration A. Case first. When the lift moves upward with an acceleration A. So this is the case. This is the lift, and weight is man is standing in the lift on a weighing machine. So weight of the man acting vertically downward, and normal reaction R acting in upward direction, and weight and the lift is moving in upward direction. So acceleration will act in the upward direction. Since lift is moving in upward direction, therefore this force is acting in downward and this is in upward direction, but the lift is moving in upward direction. So the resultant force must be equal to R minus mg. Why R minus mg? Because lift is going in upward direction, and upward direction would be taken as positive and downward direction would be taken as negative. So this is the resultant force acting, R minus mg, and resultant force is equals given by Newton's second law, m into A. So R is equals to ma plus mg, and R is equals to m is common, so A plus G. R equals to m into A plus G. So this is the formula for normal reaction or apparent wave when the lift is moving in forward direction with an acceleration A. The next case we will discuss in the next video.